Well, this is part 2, and we will be discussing about fuels and coal combustion, oxygen, CO2, and excess air. Part 2. Well, we had up till this point we have seen about the design of the combustion system. The combustion system should be such that you should have a high rate of combustion carried out in a limited furnace space. You should have minimum heat losses. Then you should have ease of operation and maintenance of the combustion system, safety of men and equipment, and controllability of the combustion process. Now we see the conditions those are prevailing in the furnace. There is a mixture of flue gases, fly ash, coal, and air. It is there in the furnace. Due to this nature of gas mixture, probability of oxygen reaching the coal particles is very small. By proper design, this probability is increased to optimum level. Now, maintaining the parameters to design values is therefore of prime importance. We see about how the coal burns in the furnace. Combustible matter is present in the fuel or coal. It is volatile matter. And secondly is solid coal carbon particles. Complete combustion takes place when volatile matter as well as solid carbon particles they burn completely. Volatile matter contains hydrogen, ethane, methane, water vapor, etc. The burning of volatile matter and soot. You see the coal particle is traveling with primary air. On entering the furnace, the particle expands and volatile material gets released. This volatile material mixes with primary air and burns out, and you will see that only the coal particle devoid of volatile matter is called soot. It will burn completely with the secondary air. The primary air is consumed in the combustion of volatile matter. Combustion of volatile matter completes within the first 40 to 50 milliseconds if primary air is able to mix with gaseous volatile material. Primary air flow rate must be such that it fulfills oxygen requirement for combustion of volatile material. Combustion of soot particles is slow as oxygen from air do not reach the solid particles as readily as that of volatile material. So oxygen transport to soot particles is by diffusion. The combustion of soot, how the soot is or how the carbon is getting burnt. Diffusion is the process in which oxygen in the air travels towards the soot particle because of difference in concentration. Oxygen reaches the soot particle because of diffusion. In the figure you see there is a high O2 concentration outside, then just near the soot particle you have a low O2 concentration, and it is in the furnace. Surrounding flue gases bulk made of mixture of air plus flue gases plus ash particles. So there is a difference in pressures of the oxygen, and that is why the diffusion will be there and the oxygen will reach the soot particle. The diffusion coefficient is directly proportional to the concentration of oxygen in the surrounding areas and inversely proportional to the particle diameter. So rate of diffusion is equal to concentration of oxygen in boundary layer of gases at the surface of burning coal particle minus the concentration of oxygen in bulk gases present in the furnace. So hence the air supplied and the coal particle diameter, they play an important role in the combustion process of coal particle. So the requirements of complete combustion. The homogeneous mixture of all the gases in the furnace at the required temperature is the most important design requirement. Homogeneous mixture ensures that coal particles remain surrounded by air mass sufficient for its complete combustion. High oxygen concentration in the surrounding air and low oxygen concentration in the boundary layer causes high diffusion rate. And then second, fuel, coal plus air, temperature and the furnace temperature. Mass of air required for complete combustion depends on mass of fuel particle. Furnace volume is selected such that 75 micron size particles, that is 200 mesh, can get sufficient mass of air for complete combustion. If particle size is more, it will get starved of air and hence will not burn completely. Resident time in corner-fired furnaces is from 1 to 2 seconds and all the particles should burn before reaching the furnace neck. How homogeneous mixture is ensured in corner-fired boilers? Admission of air from the wind box into the surface only from auxiliary air dampers. Then admission of combustion air only from the coal air dampers, and equal opening of dampers at all the four corners of the elevation. The good combustion. The objective of good combustion is to release all the heat in the fuel. This is accomplished by controlling the 3 T's of combustion, which are temperature high enough to ignite and maintain the ignition of the fuel, turbulence or intimate mixing of the fuel and oxygen, and time sufficient for complete combustion. Now we can calculate the air required for complete combustion. So the calculation of theoretical air requirement. We take a sample case wherein the molecular weights of different elements involved is given, and the elements are carbon, oxygen, hydrogen, sulfur and nitrogen. Then compounds are CO2 and SO2, and H2O is water. The chemical reactions and fuel analysis. The chemical reactions would be C plus O2 is equal to CO2. Hydrogen will combine with oxygen and form H2O. Sulfur will combine with oxygen to form sulfur dioxide or oxides of sulfur. The fuel contents. What are the fuel contents? The carbon in fuel, hydrogen and sulfur. These are the main constituents. Those are the combustion process analysis. If you analyze the process, the 12 kg of carbon will require 32 kg of oxygen to form 44 kg of CO2. The total form CO2 will be 44 kg. So 1 kg of carbon will require 2.67 kg of oxygen. So you can calculate how much oxygen will be required for 42.11 kg. It is around 112.43 kg of oxygen. Now 4 kg of hydrogen, it will require 32 kg of oxygen. So from that you can confer that 2.76 kg of hydrogen will require 22.08 kg of oxygen. And similarly for sulfur, 4.41 kg of sulfur, it will require 0.41 kg of oxygen. So the total oxygen required for complete combustion would be around 134.92 kg of oxygen. Now there is some oxygen present in the fuel as per the ultimate analysis, and so the extra oxygen that will be required for complete combustion would be 125.03 kg. The quantity of air, dry air, that will be required, because air contains 23% of oxygen by weight, so that will be around 543.60 kg per 100 kg of fuel. So the theoretical CO2 produced by volume, C plus O2 is equal to CO2, that will be equal to around 154.53 CO2. So the moles of CO2 in flue gas would be 3.512 moles. Similarly, nitrogen in the flue gas is calculated, and moles of nitrogen in the flue gas will be around 14.94 moles. Similarly, moles of SO2 in flue gas, they will be around 0.016 moles. So total moles can be calculated, and they come out to be around 18.468 moles. So the theoretical CO2 percentage by volume is equal to moles of CO2 divided by total moles dry, that into 100. So that comes out to be around 19.01% by volume. So CO2, if you measure the CO2 percentage in flue gas, and theoretically you should require 19%, but in the 19.01%, but if you measure CO2 in flue gas and if it comes out to be 15% in a sample case, then the excess air would be calculated as theoretical CO2 divided by actual CO2 minus 1 into 100. So that is equal to 19.01 divided by 15 minus 1 into 100. So it comes out to be 26.73% of excess air. Now if you measure the oxygen, instead of CO2, if you measure oxygen with the oxygen is measured at air preheater inlet as well as air preheater outlet. Suppose at the air preheater inlet the oxygen is measured at 3.8%, then the percentage of excess air would be 21 divided by 21 minus measured oxygen and whole minus 1, and that would be into 100. So that comes out to be around 22.09%. Now if you measure the oxygen at the air preheater outlet also, then the air ingress can be calculated, which will be given by the formula is oxygen out minus oxygen in divided by 21 minus oxygen out into 100, and the air ingress can be calculated. Here in this case the air ingress in air preheater is 8.86%. So thanks for watching. Please press the bell icon. Please subscribe, like and share our channel Total Output Power Solutions.